Hello everybody, my name is Borisha and we are talking about threads, rows, columns, and how we're using these built-in variables for solving some problems in matrix form. And let's say that we have one matrix with 3 rows and 6 columns. That's given in this example. So 3 rows and 6 columns. We can define it inside the program, and this is how we do it. And of course, these rows and columns must be in correspondence with some threadIdx.x or .epsilon indexes. And here we will show what is exactly the relation between them. So number of rows is represented, as we said, in threadIdx.epsilon, because when we picking up the indexes, as it can be seen here, when we picking up the indexes we are going through the epsilon axis, and that's given here. And also we said that in matrix multiplication or any kind of other problem that we use, CIJ or element of result matrix is in relation somehow with the threads and their indexes. So these indexes are in relation with these specific values for specific threads of that two-dimensional array of threads. Every one of them has its own epsilon and x indexes. X-axis is here, and threadIdx is picking up the values on the x-axis, and threadIdx.epsilon is picking up the values of rows, which is given in epsilon axis. So it's a little bit counterintuitive, but you can see if we want rows, we pick up epsilon, and that's the red here, and big note and important note. And the number of columns, we can see if we want columns to pick up indexes, we are going through this built-in variable which is representing the indexes in x-axis. So we are going for number of columns, we putting .x here, because this value in a field or struct for this let's say struct variable, .x is actually have value number of columns. You see, here are the column indexes for the let's say any kind of result matrix, and here are thread indexes or threadIdx.x on x-axis for the columns of threads. So we can see that 6 is going here as a value, and rows and total number of rows is going on a number of rows, and this is built-in variable that is picking up rows indexes. Also the values inside when we call the function. So this is defining of the variable which is struct threads per block. So we want to know how many threads we have looking inside of x-axis, and how many of them is inside of epsilon axis. So total number of threads is this number times this number. And also picking up the values from 0 to number of columns -1. So as it can be seen, yes, we have 6 columns, but from 0 to 5 are indexes for specific thread are picking up the values. So threadIdx for specific thread and calling on the kernel function is picking up on the threadIdx index.x is picking up these values 0 to 5, and in total it's 6. And also if we have number of rows 3, we are picking up these values, the threadIdx.epsilon takes values number of rows -1, so 0 to 1. The last one, of course, is given here, and the last one, of course, is given here. Number of rows -1 is actually 2, and number of columns -1 is actually 5. And when we look at these numbers, it's getting obvious. And we will give some, let's say, authentic um, uh, example, which can show in total how we sum up these indexes and to make relation and see that these indexes actually helping us to address the columns, not just columns, but addresses of in memory, where we can pick or place these values or results of some kind of things that we doing inside the body of the kernel function. So this is kernels into threads. We see one block here, and we are picking up when we call this value. So we have here will be 6 and here will be 3. So 3 times 6 is 18 in total. And let's see on a concrete example how and what is going there. This example is showing the task. We have standard IO stream for input and output on the screen and so on. This is for the device functions or GPU functions or kernel functions which are we using. We see identifier or specifier global here, so the function is called from the host to be executed on device or GPU, from CPU to be executed on GPU. Name of the function implies that we are always turning in calling of the function, which is given here. When we call the function or kernel function, we are actually making multiple copies of these functions and turning them into threads which are ready to be executed. So also we have a matrix which is result matrix where will be put some values, and here is nothing complicated like multiplying, adding matrices and so on. We are just proper index from the location starting from the beginning of this pointer. We are giving this, let's say, index or position in sense of addressing. We are giving this position to specific C function, and we see that we use here built-in variables like threadIdx.x, which is picking up specific number in sense of column, and also dimensionality of specific row, or how many elements are in specific row, and also going to specific location in given row. And this help us to make addressing of specific element because we are start to look everything from the C, which is where address where pointer is pointing to, and from that addresses we use some tricks or arithmetic for addressing specific location which we want to change, and put here put their value, which is given here, which is same as index or total index or total value of position. So that's simple function, but we want to assign some value and see how we picking up some element, some pointer on the pointer of some memory location, but in GPU, don't forget about that. We must prepare this location, or at least assign some space on GPU memory in the main program, so we can use that space and assign some exact values, which are like values of indexes for specific elements, or specific elements address in accordance to starting address C. So this was in total, this was a kernel function which we call in main program, and here we have main program. Of course, we define value which help us to make size inside of GPU memory. Inside GPU memory, where we allocate these elements and allocate the space for the elements of which are belonging to these matrix C. And also we are starting, of course, everything with the size of the space is number of rows times number of elements times size of elements which we will use. This is integer, so it means I think integer should be 4 bytes, I think, but I'm not sure. Unsigned integer, let me check. Unsigned long. I'm not quite sure, but it is 16, but not 16. It's 32 bits, and long is 64. So 8. Did I say? Yeah, 4 bytes, and long integer is unsigned integer. Long integer is 64. But why it says unsigned long? I don't know. Yes. Okay. Let's. Yeah. It's not. Doesn't matter. So we are also allocating. We're defining that resulting matrix inside a CPU memory, which we can manipulate and use. And it's integer types of elements inside, and total size of that CPU defined space inside the CPU memory is number of rows times number of columns. And also we defining some pointer, but this is pointer for the GPU or device memory, and there that pointer will show to allocate space and memory on the GPU memory, and we using this size which we defined previously here. This is the size of that space which is assigned to that pointer, but this is pointer on the GPU memory. And then we defining here also according to these values, we said that our block or threads per hour block are number of columns, which will be 6. That's according to x-axis. We going with index threadIdx.x, and with this one number of rows, when we go to epsilon, we go picking up the indexes for the rows. So this is in accordance to how we're going through the epsilon axis. So to avoid confusion, and once again to know that they are going like this for number of columns and number of rows and what is going where. So I guess we can continue. Yes, we have one block, but with 2 dimensions, .x and .epsilon of threads. So it's a 2D array of threads. And as an argument, we are putting this pointer to the allocated GPU memory. Also, we have something to synchronize, CUDA device synchronize, to synchronize this execution of assigning of these elements. And then when we finish that, yes, we didn't have any kind of input matrices. We just allocated something, and we providing that values from the device memory to the host memory, as it says in specifier here, with the size of yes, size. And then we are writing down this matrix C, which is given here. So if we want to go through the rows, we're going now with the I. Don't forget and don't make this confusion. Also, and for every rows, we going through the elements of that rows, which are given in columns. And putting on the standard output, we putting in a familiar manner I times and number of columns plus a yacht, and then make a separation. And when we finish of writing down of all elements in that row, or when we pick up all indexes for that row in sense of yacht, it's a little bit now counterintuitive what we previously talked here. It's a different manner, which we also said here. Yes, I is going and picking up 0, 1, 2, and the columns, that's now in sense of yacht, or picking up from 0 to 5. So this is for the writing this standard. Yeah, after we finish one row, we're going to next row to write down, and we pick up this another value with this increment, and so on and so on. And after we finish this writing, then we are freeing the pointer to the device memory, which is given here. We're just checking here, is it successful or not, and then we are return 0. So we expect to every element actually pick up, every element of the matrix C actually pick up its own address in accordance to the C. So for the threadIdx 0 and threadIdx.x, epsilon and x, 0, 0, we have C 0, so that's the starting address, and the value inside will be that index, which actually representing the memory location, which help us to do and check and pick value of that exact memory location. So and then we are going through the others. Also, when we're writing this and how we addressing here, don't forget, let's say it says a number of let's say number of row times total number in every row. So that means that here, so if this is number of row, and we're picking up the number of columns or number of elements in that row, to know how many addresses to skip, and then with yacht index, which is also plus with that, with yacht index, let's say index yacht, we from the starting of that row we picking up specific elements. So just to know how this address calculation works. Okay, give me again the picture of picture of this. So this we pick up the addresses of specific rows, we're skipping up a number of columns for all previous rows, or jumping over these addresses to catch the specific address of beginning of the specific row. I must do the video which in more detail explain this, but it's common sense. Everybody who works with the C or C++ knows this. And also this is to pick up specific elements. And I think there is nothing more left to be done except to execute or to compile this program and execute it, so we can see the results. And the results shall be that we are picked up all elements, that all elements of matrix are actually picked up integer value of index of their address in accordance with the C. So we are compiling, now talking, we are compiling. We compile it, let's execute, and let's see the results. Yes, so we can see that we picked up so 0, that every element picked up every element of matrix C picked up its own index, which help us to find that element in memory from the specified location of pointer C. So for the first element is 0, then we are going with this, and also next element. So this also correspond in correspondence with indexes, or where is the specific address in accordance with this. So that's it. To play a little bit and let's say do it with the threads and blocks, we can pick up here, let's say we can do it with 2 blocks. Block time. Yes, but I don't have. Yeah, I don't have time for doing. If I put 2 blocks, then I need to put here index and calculate index for specific. But I can do it in the next example to show how it's done. And the main topic of this, let's say, exact examples is to know how to use these arithmetics to go up and down and do the 1, parallelism, and 2, how to do these address arithmetics in sense of thread indexes, block indexes, and so on. So it's enough for now. This was a semi theoretical, semi practical video, which includes both. So I think it's a good thing to be more, let's say, to go more like visual, and then go to the program, to then we avoid to be too much monotonous with this example. But enough talk. That's it for now. See you in next video.